Back, so let's summarize again what we now know. You should now know what potential energy is. So energy of position. You should also know what kinetic energy is, energy of motion. And now we have discussed what work is. So the force that you apply multiplied by the distance that you travel is going to be equal to work. And then we know that work changes the energy of a system. Now the question is, what would happen if there is no external force acting on the system? So if there was no force, then F would be 0. 0 times anything would be 0. So there would be 0 work acting on the system. And so then that would mean that 0 would be equal to the change in energy of the system. But the change in energy of the system would be energy final minus energy initial. And then if you were to take this over to the other side, you end up with the energy that you start with has to equal the energy that you end with. And so this thing here is going to be called conservation of energy. This should sound familiar because when we did our lessons on momentum, we found that if there was no external force acting on a system, then momentum was going to be equal, the change in momentum was going to be equal to 0, and then the momentum that you started with was going to be equal to the momentum that you ended with. Well, this is going to be the energy you start with is going to be equal to the energy that you end with. Now, what kind of energy could it be? Well, it could be any kind of energy. Could be mechanical energy, could be thermal energy, could be electrical energy, but we're going to keep it simple. We're going to stick to mechanical energy. And so we're going to say that the energy E is going to be equal to the potential energy of the system plus the kinetic energy of the system. Now, these things can change, but when you add them together, it doesn't change. So in algebra, you should know that 7 is going to be equal to 6 plus 1. But you should also know that it's going to be equal to, let's say, 5 plus 2. So do you see that this number here is getting smaller, but in order to compensate, this number here has to get larger. So imagine that one of these numbers is the potential energy, and then the other number is the kinetic energy. When you add the two numbers together, you get some total energy that doesn't change. The energy you start with is equal to the energy that you end with. So here's an example. How is potential energy turned into kinetic energy in each of these pictures? So the first picture is of a roller coaster. So the roller coaster is going to be pulled up to the very top of the first hill with an engine. So the engine is going to put energy into the system. And that's going to raise it to a certain height. Now, once the roller coaster is at the top of the hill, the engine stops working, okay? And so now all you got to do is get that roller coaster moving downhill, and do you see it's going to be losing height as it's falling. So what else is it losing? Potential energy. So the potential energy is getting smaller. So what do you think the kinetic energy is going to do in order to compensate? It's going to get bigger. Okay, now if the kinetic energy is getting bigger, kinetic energy depends on the speed. So if the kinetic energy is getting bigger, what's the speed doing? It's getting bigger. So as the roller coaster is going down the hill, it's going to be going faster and faster. Now, when it's at the bottom of that first hill, how much height does it have? 0. So it's on the ground when it gets to the bottom, and so it has no height, so it has no potential energy. So where did the energy go? It's now all kinetic energy, but it doesn't just stay there. So what does the roller coaster do? It's going to start going up that first loop-de-loop. So as it starts to go up, it's gaining what? Height. So it's gaining potential energy. So if this number is getting bigger, this number has to get smaller. So it starts to slow down the higher up it goes. And then when it's at the top of the loop-de-loop, it both is moving, so it has kinetic energy, and it has a height, so it has potential energy. But when you add these two numbers together, it should equal the energy it had when it was at the top of the first hill. Now, we're not taking into account friction. So it's true that the wheels are going to be rubbing up against the track. That's going to cause heat. The heat is going to go into the air. So the roller coaster really is going to lose some energy due to heating of the track. But let's just assume for the sake of argument it's not doing that. So we're going to say that energy is being conserved anywhere along that amusement park ride. Now, what about the picture that's next to it? What do you think that's a picture of? That's a picture of a wrecking ball destroying a house. So if we were to make a picture here, here is the wrecking ball, okay, and then here's the ground over here. And notice that the wrecking ball, when it swings to its maximum height, it's going to have a certain height. So let's say that's h. So that's going to be the distance from here down to here. Okay, now it's going to start to fall into the building. And so now let's say that the wrecking ball is now down here. And so here's the wrecking ball. And notice the h has done what? The h got smaller. So it's a smaller distance from here down to here. So what does that tell you? Over here, it has a lot of potential energy because it has a lot of h. When it's all the way out, is it moving? No. So it has 0 kinetic energy when it's out here. Now, as it's falling, the potential energy is getting smaller and smaller. So what must be happening to the kinetic energy? It's going to be getting bigger and bigger. So by the time that it's down here, the energy it had, which was potential, is going to be turned into kinetic, and then that kinetic energy is what's going to cause the house to be smashed. So here's a sample question. A roller coaster has 10,000 joules of energy when it's at the top of its first hill. Explain what happens to this energy as it travels around the track. So the energy is initially in the form of potential energy. As the roller coaster falls, it's losing potential energy, but it's gaining kinetic energy. And when you add the two numbers together, it always has to add up to the same number. So therefore, the total energy is going to remain at 10,000 joules anywhere on the track. Now, again, that's assuming that there's no friction going on. Okay, here's a math one. So you've got a wrecking ball, and the wrecking ball has a mass of 2,000 kilograms. Okay, and it's hanging from a rope, and initially it has a height of 18 meters off the ground, and then it's going to smash into the building. So the question is, what's going to be the speed of the ball when it hits the building. So just like we did momentum problems, we're going to begin with the total energy before has to equal the total energy after. Okay, now what can that energy be? So the total energy before could be either be potential or kinetic, and then afterwards it can be potential or kinetic. So then the next step is, well, what is potential energy? mgh. What is kinetic energy? It's going to be this. Okay, but do you notice I put a lot of subscripts on it? So I talked about the energy when it's at the top, and then the energy when it's at the bottom. Okay, then the next step is to cancel out my m's. Do you see that every one of these equations has an m in it? So I can cancel it out. Now what does that mean? That means that the mass of the ball here really doesn't make any difference. It's going to have this exact same speed when it hits the building, whether this was a 2,000 kilogram wrecking ball or whether it was a ping pong ball. Now that, again, that's assuming no wind resistance. So if you ignore all of those other factors, it would have exactly the same speed when it smashes into the building. Okay, then what's the next thing that I can do? So I canceled out my m's out of all of those little pieces there. But then the next thing I said to myself was, when the ball is up here, it's not moving. So therefore, the speed up here is going to be 0. And then when it smashes into the building, it has no height anymore. So therefore, it has no potential energy when it's down here. So this part is 0. So it simplifies greatly there. So essentially, we're taking all potential energy up here, and we're turning it into all kinetic energy down here, and then you solve it for the letter V. So that would be something that I would expect you to be able to do. Another interesting thing about it is, imagine that you just took a regular ball and you lifted it up to 18 meters, and then you let go of it so that it falls straight down. How fast would it be going when it hit the ground? That exact same number. So what's the difference? So if you took something from 18 meters and you let it go, its speed is going to be straight down when it hits the table. What happens in the wrecking ball? The speed is sideways because it's been turned into sideways motion because of the string up here. Pretty interesting, right? I hope so. All right, let's take a break. When we come back, let's talk about the laws of thermodynamics.